It is time to learn all about atoms.
Welcome to our deep dive today. We're going to be taking a look at atoms,
Okay.
those fundamental building blocks of, well, everything, really.
Right.
And
Sounds good.
we'll be breaking down the history, the structure, and just all the implications of these tiny particles.
It's amazing to think that the idea of atoms has been around for centuries. Way before we had the tools to actually study them directly.
Yeah?
Like the ancient Greek philosopher Democritus, he came up with the term atomos, which means uncuttable because he imagined these like indivisible units of matter.
It really shows you how curious humans are, like always trying to figure out the world at the smallest level.
Yeah.
But of course, Democritus's idea was philosophical.
Mm-hmm.
It wasn't until the early 1800s that John Dalton, through his work in chemistry,
Yeah.
brought the concept of atoms into science.
Dalton was so meticulous. His observations of how elements combine to form compounds, it revealed a really key insight.
Okay.
They always combine in specific ratios of small whole numbers. For example, he found that tin could combine with oxygen in 2 different ratios, leading to different tin oxides.
Interesting.
And this consistent pattern that he saw across multiple compounds pointed to this fascinating conclusion.
What's that?
Each element must be made up of fundamental units, atoms, that combine in whole number ratios.
So Dalton's work really established the atom as a scientific concept.
Yeah.
But the picture of the atom, it was far from complete.
Right.
The discovery of the electron in 1897 by J.J. Thomson added a whole new layer of complexity.
Thomson's experiments with cathode rays showed that these rays were made up of negatively charged particles,
Okay.
much lighter than even the smallest atom, hydrogen.
Wow.
This discovery totally changed the view of the atom as a simple, indivisible entity.
It must have been a revolutionary moment in science. How did scientists try to reconcile this new particle with the existing model of the atom?
Well, Thomson, he proposed the plum pudding model, where negatively charged electrons were embedded within a positively charged sphere. This ensured the atom's overall neutrality.
So it was kind of like a creative way to fit this new piece into the puzzle.
Exactly.
It seems like each new discovery
Yeah.
just brought up more questions than answers.
Definitely.
And the quest for a deeper understanding led to Ernest Rutherford's famous gold foil experiment in the early 20th century. He bombarded a thin sheet of gold foil with alpha particles, expecting them to just pass through with minimal deflection.
Right.
But what he observed was far more interesting.
What happened?
From what I understand, a significant number of those alpha particles were deflected at sharp angles,
Yeah.
some even bouncing straight back.
Yeah, exactly. This unexpected result just couldn't be explained by Thomson's diffuse plum pudding model. The large deflections, they implied a concentrated positive charge within the atom, something capable of repelling those positively charged alpha particles.
So this is where the idea of the nucleus comes in.
Absolutely. Based on these findings, Rutherford proposed a revolutionary new model, a tiny, dense, positively charged nucleus at the atom center, with electrons orbiting around it.
Like planets around the sun.
Exactly.
This was a huge change in how we understood atomic structure. But even with this groundbreaking model, the story of the atom wasn't over yet.
According to classical physics, electrons orbiting the nucleus should continuously emit radiation, lose energy, and eventually spiral into the nucleus.
Oh.
But that obviously doesn't happen. Atoms are stable, which means something was missing from what we understood.
So what was the next piece of the puzzle?
Well, in 1913, Niels Bohr, he built on the work of Planck and Einstein on the quantization of energy, and he proposed a model that addressed this problem.
Okay.
He suggested that electrons could only exist in specific orbits, or energy levels around the nucleus.
So you're saying their energy was quantized,
Yes,
not continuous like classical physics would suggest.
exactly. And electrons could jump between these allowed energy levels by absorbing or emitting photons of specific energies.
Interesting.
This neatly explained the discrete spectra of light, observed from different elements. Each element had a unique set of energy levels, resulting in a distinct spectral fingerprint.
It's remarkable how Bohr's model linked the structure of the atom to the behavior of light.
It was a major breakthrough, although it also had its limitations.
Okay.
It worked well for hydrogen, the simplest atom, but it struggled to predict the spectra of more complex atoms. The key takeaway, though, was this. The world of the atom was governed by the bizarre and counterintuitive laws of quantum mechanics.
It seems like every step forward in understanding the atom revealed even deeper mysteries waiting to be explored.
That's right. And as we delved further into the heart of matter, we began to uncover a whole subatomic zoo of particles, protons, neutrons, and even smaller, more fundamental constituents. Protons and neutrons, that was a big moment.
Yep.
Gave us a clearer picture of what the atom is made of, but also brought up a whole bunch of new puzzles.
It's like peeling back the layers of an onion, only to find more layers underneath.
Right.
How did scientists even begin to unravel these subatomic mysteries?
Well, early hints came from looking at atomic weights. Scientists noticed that the atomic weight of an element was often roughly twice its atomic number. Implying something other than just protons was adding to the atom's mass.
That makes sense.
And it was Rutherford, back in 1919, who gave concrete evidence for the existence of the proton.
Right.
He bombarded nitrogen gas with those alpha particles and observed the emission of hydrogen nuclei. This led him to conclude that these hydrogen nuclei, which he called protons, were fundamental particles residing within the atom's nucleus.
So the proton carrying a positive charge, equal in magnitude to the electron's negative charge, became a crucial piece of the puzzle.
Yeah.
But what about the remaining mass? That couldn't be accounted for by just protons.
That mystery was solved in 1932 by James Chadwick. He discovered the neutron, a neutral particle, with a mass almost the same as the proton.
So that completed the picture of the three basic subatomic particles that make up the atom.
Exactly. Protons, neutrons, and electrons.
Amazing to think that these three particles, in all their different combinations, form the basis for all the elements we see in the universe.
It's incredible. The number of protons and the atomic number defines what the element is. But the number of neutrons can change within an element, leading to different isotopes.
Like, for example,
Yeah.
hydrogen comes in three forms.
Right. Protium with no neutrons, deuterium with 1, and tritium with 2.
So isotopes of an element
Yeah.
have the same atomic number, same chemical properties,
Yeah.
but differ in their atomic mass because of the different number of neutrons.
That's right.
But how do these isotopes behave differently?
Well, while they're chemically similar, isotopes can have different physical properties, especially those related to mass and radioactivity.
Okay.
Some isotopes are stable, while others are unstable and undergo radioactive decay.
So radioactive decay is the process where an unstable isotope transforms into a more stable form by emitting particles or energy.
Yeah,
And there are different types of radioactive decay.
Yeah, like alpha decay, where an alpha particle, basically a helium nucleus, is ejected from the nucleus, and beta decay, which involves a neutron transforming into a proton, or vice versa, accompanied by the emission of an electron or a positron.
These tiny atoms are so active, constantly going through transformations at the subatomic level.
It's a dynamic world down there, and the energy from radioactive decay, it can be used for lots of things, from medical imaging and treatment to power generation and research.
We've built a pretty complete picture of the atom, but I have a feeling there's still more, especially when we consider the world of quantum mechanics.
You're right. While the Rutherford model was a good start, it was still rooted in classical physics, imagining electrons orbiting the nucleus like planets around a star.
Okay.
But quantum mechanics reveals a much more nuanced and counterintuitive reality.
How did quantum mechanics change our understanding of the atom?
It completely changed how we think about electrons and their behavior. Instead of fixed orbits, we now have the concept of electron clouds and atomic orbitals.
I've heard of those terms, but I'm not sure I really get them.
Okay, imagine a cloud surrounding the nucleus, denser in areas where it's more likely to find an electron. These regions of high probability are what we call atomic orbitals. They are 3D shapes that tell us the likelihood of finding an electron in a specific spot around the nucleus.
When we're moving away from the idea of electrons whizzing around the nucleus in neat, predictable paths.
Exactly. Instead, we have this probabilistic view, where we can only talk about the likelihood of finding an electron in a particular region at any given time.
Like trying to pinpoint the location of a hummingbird. You can describe the general area where it's likely to be,
Right.
but you can't say for sure exactly where it is at any moment. This shift to a probabilistic understanding seems to bring uncertainty to our description of the atom.
You're absolutely right. This uncertainty is a core principle of quantum mechanics, the Heisenberg uncertainty principle.
What does the Heisenberg uncertainty principle tell us about the atom?
It says we can't know both the position and momentum of an electron with perfect accuracy. The more precisely we know one, the less we can know about the other. It's like nature is setting a limit on our ability to measure these things at the same time.
It's mind-blowing. At the subatomic level, reality itself becomes uncertain.
It's a profound concept, and it
Mhm.
changes how we understand not just atoms, but the nature of reality itself. We have to abandon the deterministic view of the universe, where everything can be perfectly predicted, and embrace a world where probability and chance play a fundamental role.
If we can't pinpoint the exact locations of electrons, how do we even describe the structure of atoms and predict how they'll behave?
That's where the power of quantum mechanics comes in. Even though we can't know exactly where electrons are, we can use complex math equations like the Schrödinger equation to figure out the probabilities of finding electrons in different regions.
Those atomic orbitals.
Exactly, the shapes and energy levels of those orbitals, derived from these quantum mechanical calculations, give us a way to understand the atom's behavior.
So those orbitals, each with a specific energy level, determine how electrons interact with each other and other atoms, forming the basis for chemical bonding. And all the amazing molecules and materials we see around us, these tiny atoms, governed by the laws of quantum mechanics, they're responsible for everything we see in the universe.
It really is amazing.
We've gone through the structure of atoms, their subatomic particles, the idea of isotopes, and even touched on quantum mechanics.
Right.
But there's one last thing to uncover:
What's that?
the origin of atoms themselves.
Ah.
Where did they come from? I'm guessing the Big Bang played a big role.
Absolutely. In those early moments after the Big Bang, the universe was incredibly hot and dense. All those fundamental particles, quarks, electrons, they were just swirling around. And as the universe expanded and cooled, those particles started combining.
So the cooling allowed the first atoms to form.
Exactly. Protons and neutrons came together to form the nuclei of the lightest elements: hydrogen, helium, and a little bit of lithium. This process is called Big Bang nucleosynthesis, and it created the first elements in the universe.
So the first atoms were created in the Big Bang. What about heavier elements? The ones that make up our planet and even us?
That's where stars come in. Stars are like giant furnaces, powered by nuclear fusion, where lighter atomic nuclei fuse together to make heavier ones.
So stars are like element factories,
Yeah,
churning out heavier elements from hydrogen and helium.
exactly. In the core of a star, hydrogen nuclei fuse to form helium, releasing a ton of energy, which makes stars shine. And as stars get older, they can fuse helium into carbon, carbon into oxygen, and so on, building up heavier and heavier elements.
But I imagine there's a limit to how heavy an element a star can create.
You're right, stars can produce elements up to iron through fusion, but for anything heavier, you need something more dramatic.
A supernova.
Exactly. When a massive star runs out of fuel, it collapses and explodes as a supernova. This explosion is incredibly powerful and creates the conditions for forming elements heavier than iron.
So the gold in jewelry, the uranium in nuclear reactors, all created in these cosmic events.
It's pretty humbling.
All the elements that make up our world and our bodies were created in stars and scattered by supernovae.
We're made of stardust.
It's amazing how everything is connected. This web of cosmic processes led to the elements and to us.
And it all starts with these tiny particles, the atoms we've been talking about.
This deep dive has given me a much deeper appreciation for the universe, from the smallest atom to the vast expanse of the cosmos.
And the journey of discovery never ends. As we keep exploring atoms, we're pushing the boundaries of what we know, exploring new forms of matter, unraveling the forces that govern the universe, and maybe even finding new secrets that will change our understanding of reality.
Thanks for joining us for this deep dive into the atom. Hopefully this exploration has given you a better understanding of how the universe works, all from these tiny building blocks of matter. Keep exploring, delve deeper into the ideas we've talked about, and seek out new avenues of understanding. The world of the atom is a gateway to a universe of wonders waiting to be discovered.